Now there are a number of different components that we use in the local area network. We have repeaters. Now a repeater doesn't really do much other than lengthen the run of the cable. Remember I told you the electrons get tired as they're going down, right? The attenuation of the signal. Well, I can hit a repeater, and when the repeater sees it, it regenerates the signal and sends it back out again. Now, this is different than a radio frequency repeater. Often a radio frequency repeater takes a radio frequency and repeats the signal, regenerates it, but on a different frequency. There's no such frequency translation here. It's just literally re-energizing that electron to send it a further distance. We saw ways of interconnecting devices on what we called hubs. It's kind of like having a power strip plugged into the wall. We shared one signal with everybody. Then we had bridges, which allowed us some translation. And like I said, I'm going to diagram these for you and try to add in that Ethernet part for you as well. We improved the speed of bridging into switching, what we call transparent switching, but better off for us to call it layer 2 switching, which means we're switching things at the Ethernet. Since I'm using Ethernet as my example, we would switch things based on their MAC address. Look at the MAC, know where to send it. Now, from there, we could also get into larger networks, right? I said if that gets too large, we need to break it up. Well, we broke them up with routers. And in routers, we were able to create new little networks of areas that could still talk to each other, but we didn't make the distinction based on the actual MAC address, but we looked at the IP address. Now, we have some routers, and that's a layer 3 function. Some routers and some switches can make decisions not only on the IP address, but they could also look at your transport layer address. Are you using TCP? Are you using UDP? In fact, if I had a router that worked at layer 4, what I would see is that, or a switch, at that point we're getting ambiguous with what they do. And when I get that information and I see that you want to hit a destination port 80, and I know that's a web server, instead of even looking at the address, I can just say, oh, TCP port 80, here it goes to the web server. And we have some that can do that decision on all of the upper layers of the OSI model. We call them multi-layer switches. Now we also have gateways. And for those of you who've configured an address on your Windows machine, that's not a gateway. I mean, that's what they have you type in, gateway, but that's not a gateway. That's actually the information they want as your router. A gateway is something that does protocol translation. In the days when Microsoft was getting larger, Novell was already the king of the network, they used different languages. Remember I told you that. They had a different set of addresses and a different transport layer protocol. They just spoke different languages. So a gateway was a translator. For my Microsoft machine to be able to talk to that Novell machine, I would send it to a gateway who would translate it for me into something Novell understood and then translate it back as it came back to me. Anyway, those are some of the components you would see in the local area network. Well, to kind of wrap up our little discussion, there was a time we had these little coax cables, and we had really thick ones, so we called it thicknet. And we'd tap into it with these smaller coax cables, and it would be there that we'd put all the computers, hook them into this network. And we called it a bus network, and it was Ethernet. And the features of a bus is that if one person sent a little communication out, it would follow down this bus, and everybody would hear it. So it's kind of like a party line. Now, Ethernet is a carrier sense multiple access, we said, with collision detection. So a computer wouldn't transmit anything, carrier sense, unless they didn't think anybody was out there. But they also didn't have to wait turns like we did in Token Ring. So if it turned out, that as I was doing this, if it turned out that maybe computer 1 and computer 2 were listening, and they didn't hear anything, and they decided they'd talk about the same time, well, that's because it was multi-access. They could. But unfortunately, their signals would electronically collide and make garbage out of themselves. And that garbage that we would hear would be an indication of a collision detection, which let these guys know that if they heard the collision, that they would have to rebroadcast. But that was the breakdown of Ethernet. And that was the bus network. Then somebody decided, hey, let's build a device. And they built a device, and they changed the cable specifications to these twisted pairs. And this device had little RJ45 jacks. And you would plug your computer into that little port. And now, what was happening here is that in that old bus network, if the cable went down, everybody lost their network. Here, whoever's cable died, they're the only ones that would break. And we called it a star network. It's a hub. But it operated the same as a bus. If somebody sent a transmission in, everybody else would hear it. And of course, if we weren't careful, if more than one person's talked at the same time, they'd have a collision. In fact, we considered this whole thing one big happy collision domain, because we could collide at any point in our communications. Now, having said that, what we saw was this guy that developed a technology known as a bridge. And that's the symbol they used for their bridge, which was a representation of the Golden Gate Bridge in the city that his company was named after, Cisco. And what happened was the goal here was to connect, and this is not factually completely the same. I mean, the story's close. The function I'm about to describe is true, but I'm just, putting it into a story, right? A little, leeway there. And so what he wanted to do was to be able to communicate with somebody that was on a different network. So he was on Ethernet, and let's just say they were on Token Ring, all right? And so whoever this other person was that they wanted to talk to. And so the problem is we had to translate one type of network to another. And so this bridge would do that for us. It would translate. But what we saw is when the packets went into the bridge, they were stored in here in memory while it was being translated. And if the other side talked at the same time, their traffic was stored in memory. And then when the translation was done, they'd send out their information. But guess what? No collision. Okay? That's awesome. Because now that there's no collision, we got rid of one of the biggest drawbacks to hubs. In the hubs, we were sharing our bandwidth. Nobody truly got all the speed. Now we could. All right, so then what about taking this collision domain that was all Ethernet, and let's put the bridge in that place, and let's just do all Ethernet. I mean, why not have no collisions, but no translation? And they said, well, we could build a device in hardware that could just do that information, since it doesn't have to, be translated. And that device is what they called a switch. And so now, with every port on a switch, the same things happen, right? Traffic comes in one port, traffic can come in another port, but it doesn't collide because internally the switch takes care of it all, and does this bridging transparently, meaning you came in Ethernet and you went out Ethernet. And so now we have new collision domains. In fact, every port on the switch was its own collision domain. So that gave us a switched bandwidth. Now, as I take these switches and start growing the size of my network, one of the things that a switch did is that it took broadcast traffic, and by the meaning of broadcast was that if a broadcast came in, it would have to send it to everybody that's in the network. And once we started getting more and more PCs, the amount of this broadcast traffic was getting larger and larger, and it became a little hard for things to be able to communicate. So we said, why don't we divide the network? So they did. They put a new device in here that they called a router. So there's my router. And that router would separate it so that now broadcasts would only be contained in one location, and they wouldn't bother each other. The problem was how do I get from one side to the other? Well, we came up with a logical address solution with IP addresses. So now when I try to reach somebody by their IP address, because down here, I didn't say it, down here on the switch, we were using their MAC addresses for decisions. That's layer 2. This router is using layer 3 to be able to communicate that same information. So now if I needed to get to the other side, I just hit the router, it would look at the IP address and deliver it to the next broadcast domain, and there the switches would look at the MAC address. Some devices, because a router traditionally in the day, 15, 20 years ago, was slow, especially by today's standards. So what they said is, they said, look, I need to keep the same speed of switching, because switching was fast. Still, it's very fast. And they said, we want the same speed of switching that we did before, but I still want the separation of a router. In other words, I want both. And so what they did is they made a device that could do layer 2 switching, layer 3 switching, and they called it a multi-layer switch. So it was another solution that we had. So I think what I've done here, hopefully, is at least give you some ideas about the different types of networks, the different types of devices, not all of them that I listed here, and kind of also give you the Ethernet interpretation as far as what they're doing. And I'm hoping that kind of helps clarify both some of the Ethernet stuff, clarifies the functionality of the different devices, and of course a little review there of the lower layers of the OSI model.